curve, right? So a numeric integral of a function, we want to get the area underneath the curve. So that's helpful when we need to know something about the area underneath the curve. But it's not necessarily helpful if we have some sort of function and I want to actually integrate that function. So say I have an acceleration, a function for acceleration, and I want to determine the velocity, I want to determine the position, the functions of velocity and the functions of position. So what those equations actually are. So that's another type of integration, but it's kind of more on the function level than on kind of the real numbers and kind of the actual values. Similar related concepts, but you get different results. So when we calculated integrals or the area under the curve, we got a number. When we solve what are called ordinary differential equations, we're going to be integrating, we're going to be doing numerical integration, but we're going to be getting back kind of functions or relationships with respect to our variables. So so today what we're going to do is we're going to kind of walk through this handout that I gave to you guys. There are blanks that you should be filling in as we're going along. And these are going to be kind of your notes for these differential equations, for the solving ordinary differential equations. So our question today is focused on this simple pendulum. So to simulate the motion of a dynamic system, such as a pendulum, so like the one I have drawn here on the handout and the one that I'll draw on the board. We need to, so in order to kind of simulate the motion of any sort of dynamic system, it could be a mechanical system, it could be an electrical system, some sort of system that you have, you want to kind of simulate what happens in that system, then you need to use what are called your equations of motion, or the equations kind of the system itself. When we're talking about a mechanical system like a pendulum, we get our equations of motion from our free body diagram. So we draw our free body diagram and we get our equations. We say, sum of forces is equal to mass times acceleration, and we get our equations related to the acceleration of that pendulum, right? So we hopefully could all, figure out what our equations of motion are for a really simple problem like a pendulum. And so what those equations give us, so we have our equations of motion in generic terms. We have sum of our forces is equal to mass times acceleration. So that gives us acceleration. So what happens if I want to determine the velocity and I want to determine the position of my pendulum? Can I get that from this equation of acceleration? Yes. What do I have to do to that equation of acceleration to be able to get velocity and position? Integrate it. So if I take the first integral of this equation, I'm going to get velocity. If I integrate one more time, or take the second integral of that equation, I'm going to get the position of my pendulum. So that requires me to do some integration. And so this is where kind of solving these types of equations comes in handy in mechanical systems, is that we're often getting equations that are related to acceleration or some derivative of the variable that we're interested in, but we actually want, say, the position or something more simple from our system that we have. We're not often, well, sometimes we are. Sometimes we're interested in the acceleration. A lot of times we're interested in the position or where that pendulum actually is in space. So if we have our equations of motion for our pendulum here, this is what we call an ordinary differential equation. And so you'll often see, let's write this down here. So this is what we call an ordinary differential equation. You'll often see people abbreviate this as an ODE. This is meaning that we have kind of one what is called independent variable. So in this problem, our dependent variable is our position of our pendulum. So that's the thing that we might integrate to be able to get acceleration. So we're going to take position, and we're going to take position, and we can relate that to our acceleration. And we have one independent variable, which is time. So we're going to take the derivative or the integral of all of our things with respect to time. And that's how we're going to move from position to velocity and acceleration, or back from acceleration to velocity to position. So in this problem, our dependent variable is the quantity that we're going to differentiate or take the integral of, which is related to the position of our pendulum, or the theta value. And then our independent variable is our time, or the thing that we're going to differentiate with respect to. So for the pendulum, we're focused on acceleration, which is the second derivative of position, right? So this is considered to be a second order ordinary differential equation. And you guys may have heard the term ordinary differential equation in your differential equations class. You may have also heard partial differential equations. So that's where you've got multiple independent variables, and you might take the derivative with respect to time, and you might take the derivative with respect to some other variable. Those are partial differential equations. So we're going to just talk about ordinary differential equations in this class. Similar concepts apply to partial differential equations. So before we jump into the pendulum, because this is a second order ordinary differential equation, a little more complicated, let's work on a really simple numerical integration example. So we're going to use this really, really simple example so that we can kind of see what is meant by numerical integration, and how is that different from, say, analytical integration that you might have learned in your differential equations class. So we're going to start off with this really simple ordinary differential equation. So we're going to have a first order ODE, or ordinary differential equation. That's going to be dy dt is equal to 2 times t. So really, really simple in this problem. So in this problem, what variable is our dependent variable? What variable have we differentiated to get this equation? Y. So our dependent variable is y, and our independent variable is t, because it's the other one, but it's also the variable that we're going to take the derivative with respect to. So we said we've got this equation, dy dt, we're taking the derivative of the dependent variable with respect to the independent variable. So that's kind of just establishing that. We said it's a first order differential equation because we only took the first derivative of y with respect to t. We're not dealing with the second derivative or any other derivatives. We're just dealing with that first derivative. So that's a first order ordinary differential equation. And so because this equation is really, really simple, we can easily do what's called analytical integration of this function. So hopefully you kind of remember from differential equations that you can look these kind of things up in a book or a table kind of thing. Like how do we take the integral of these really kind of generic simple functions? And so we can easily find the analytical solution. So if we say we want to calculate or determine the analytical solution of this ordinary differential equation, we want to take the integral of this ordinary differential equation. So that would give us y as a function of time is equal to the integral of our dy dt equation 2 times dt. We got to remember, or 2 times t, we got to remember to put our dt out there to the right-hand side when we're taking an integral. So like I said, when we're finding these analytical solutions of these really, really simple ordinary differential equations, we can go look up something in the back of our differential equations textbook, and it tells us what the form of this analytical solution should look like. So the general form says that the integral of some variable x to a power n dx would be equal to x raised to the power of n plus 1 divided by n plus 1 plus some integration constant c out there on the right hand side. So if I want to apply my general form for the analytical solution of this derivative to find y of t, what's my y of t actually going to look like? How would I write that? So I need to kind of translate what I have here to this generic form here. So on the top of my fraction, I want, huh?
It would be 2t to the power of minus 1.
So 2t to the power of
1 minus
1 plus 1. So my original exponent on my t is a 1. So that was what I end up substituting in for n. And then on the bottom, I'm also going to have what?
1 plus
1 plus 1. And then I still have my bothersome plus c over there on the right-hand side.
Then the 2 will go with the 2.
So if I simplify this down, I get a 2 on my numerator. I end up with a 2 on my denominator. So I end up with y of t is equal to t squared plus c. Right? So now if I want to get rid of that c, what do I have to do? Remember? We have to say that?
Initial values.
We have to have initial values or initial conditions for our problem. And that's going to help us solve for that value of c. So we can get rid of this kind of extra thing that's floating around. So to solve for c, we need that initial condition. So we're going to use an initial condition that says y at t of minus 1 is going to be equal to 1. So if we plug that now into this equation, we say y of minus 1 is equal to minus 1 squared plus c. This gives us a 1 is equal to 1 plus c. So my c is equal to 0. So if I write my final analytical solution for y of t, I just say y of t is equal to t squared. So my final analytical solution for this problem is y of t is equal to t squared. So pretty simple. We can do this by hand, and it's really easy to figure out how we can find this analytical solution. So now what we'll talk about is how do we actually do this numerically, and can we compare the two and make sure that we get the same result numerically that we do with this analytical solution. So there's lots of different ways to perform numerical integration of an ordinary differential equation. We're going to learn how to perform one of the simple methods, and then we're going to learn how to use built-in MATLAB functions to do some of the more complicated, more accurate methods. So we're going to learn a really simple method. We're going to quickly see that that's not a super accurate way to calculate or to do numerical integration, but it is a really easy way to kind of understand what's happening in the background. And then we'll kind of use these more sophisticated methods and apply that to the final project. So the first, or the numerical method that we're going to learn is what's called Euler's method, and it's a really, really simple way to numerically integrate an ordinary differential equation. And so when we do that, when we do numerical integration, we need to, or we're going to attempt to try to pick the new value of our dependent variable. So in this case, the new value of y, the new value of y from kind of the previous value of that variable y. And so to perform that, we only need the information about our ordinary differential equation. So we only need this equation here, this dy dt equation, and we need initial condition of the system. So just like we did kind of over here where we needed that original form of the equation, the original dy dt, and then we needed our initial conditions to figure out what that integration constant C is. It's kind of the same thing when we do our numeric integration with Euler's method. So let's see, where am I going to write this? I don't know what they did to the boards over break, but somehow they're extremely hard to erase today.
I mean, the green marker is hot today.
Yeah, but usually it's better. Today the boards are all like splotchy, and I don't know what they did, but not a fan. So whenever we want to calculate or apply Euler's method, we kind of need the generic form for our Euler's method, and this is just one simple equation. So our Euler's method general equation is y sub I plus 1, which is our new value of our dependent variable, is equal to the old value of the dependent variable, y sub I, plus a function of t sub I and y sub I multiplied by h. So this function here is really the slope, or it's our first order ordinary differential equation. We take the first derivative of a function, and we get the slope of that function, so that's our dy dt equation over there. And then the last thing that goes in this equation is our h, which is what's called a step size, and kind of depending on how we pick that h value, it either improves or reduces the accuracy of our integration method.
So what's the inside of ti?
F of t sub I and f of y sub I.
Okay.
So at every time, as we're doing our integration, we're going to have a value of y, our dependent variable, and we're going to have a value of t, our independent variable. So when we're applying this equation, we're going to be kind of stepping through time. So we're going to start at some initial time value, and we're going to be going to some sort of final time value. So we kind of need to decide over what range we want to integrate over. So just like when we were taking the integral underneath, the area underneath the curve, we need to say we want to start at some time value and finish at some other time value. The same thing applies when we're kind of numerically integrating ordinary differential equations. We've got to do it over some sort of time span. So we're going to say for this simple example, we're going to integrate over t over the interval from -1 to 1.
So this is xi and y.
So this is going to be the first and the last time values, the first and the last ti values, t values. And then we have to figure out what the y values are based on this equation here. So we also need our initial conditions. So before we kind of start applying our Euler's method, we need our time span we want to integrate over, and we also need our initial conditions. So we're going to use the same initial conditions that we used on the kind of analytical solution. So at time is equal to -1, we're going to say that our y value is equal to 1. So now if I want to apply this equation over every time value between -1 and 1, what kind of MATLAB code am I going to need to write, do we think? A for loop. So why might we need a for loop? What would be the reason we would want a for loop? Right, we want to repeat the calculation over and over and over again. Same calculation, we want to repeat it over our entire time span. So very, very similar to the way that we did integration and the way that we did differentiation. We're talking about trying to find those numeric values. It's kind of the same concept. We're going to need a for loop to help us repeat and kind of step through time or step through some sort of variable, our independent variable, step over a whole bunch of values of that independent variable. So let's see if we can write a simple MATLAB code to solve this, or apply this Euler's method to solve our simple first order differential equation. So I'm going to go ahead and make a script to do this. And at the top of my script, I'm going to do my housekeeping. So we'll clear out our command window, our workspace, and then close figure windows. And then I'm going to jump into kind of setting up my problem. So as I said here, we need to establish kind of what the time span is that we're going to integrate over. And we also need to specify our initial conditions. So those are kind of good things to establish or start with at the top of our script that we have. So if we want to create t, which is going to be our time vector, and I want the values to go from -1 to 1, I want that to be a vector. I want it to have a whole bunch of values between -1 and 1. And so we can pick that. That's up to us to kind of pick that value. And how many values we put into that vector is really going to help us, or kind of it's going to make our lives easier if we pick kind of the increment between all the values in our t vector to be what we want this h to be, or to be the same as what this h is. It's just going to make our lives easier. So what I usually do is at the top of these scripts is that rather than kind of the first thing I do is my t, is I actually determine what my h is, or my step size. So I set my step size h equal to some value. So let's start off with an h of 0.5. And we'll talk a little bit more about how we might pick that in a minute. So t, we said we want to start at -1, and we want to go up to +1, and we want to increment by values of h, or values of 0.5. So what MATLAB function, or what kind of MATLAB code should we use to help us create that t vector in that way? Colon operator. So if we use linspace, we have to tell MATLAB how many values we want in our vector, which we could figure out, right? But it's easier if we just use colon operator because we already know what that step size or that increment is. So we're going to start our t vector at -1. We're going to colon, put our h variable in there, so that we only, if we change what h is, we only change it in one spot. And then we say that we want to, our finished value is going to be +1. And then we also want to establish our initial conditions. And so we're going to write our initial conditions kind of in a specific way. It's going to help us when we get inside of our for loop. So we're going to write our initial condition. And we're going to say that our initial condition is a value of y. Eventually, y is going to be a vector, because we're going to set it up with our for loop. It's going to be a vector, and it's going to have all these values in it. So what I want to do is I want to just set the first value of my y vector equal to +1, or whatever my initial condition is. So if I want to set the first value of my vector, that means I want to set the first row and the first column equal to that value. So I'm going to go ahead and say y, I'm going to call this y Euler, just because we know that this is going to be calculated from our Euler's method, and we're going to compare that in a minute to our analytical solution that we did by hand. So y Euler, row 1, column 1, is equal to our initial condition, which is 1. Do we have an x?
T, sorry.
So we have t, right? We already set up what t was. So now we're kind of ready to get into actually applying our Euler's method. So we said we're going to need a for loop to do our Euler's method, right? So let's go ahead and write our for loop. So we got a for loop, and then we got to provide MATLAB kind of the 4 things to be able to set up our for loop correctly. The first thing is our index variable. We can call it whatever we want, but I kind of like, when I'm writing my Euler's method, I think of it as stepping forward in time. So I'm going to call it step because that helps me kind of understand what I'm doing. And so I'm going to call my index variable step. And then I'm going to start step. So the first value of step, I want to be what? One, two, what do we think? So if we look at our equation, this is going to be kind of like, this is going to be our I here in this equation. Or we could, I guess let's go ahead and call this index variable I, just for simplicity's sake, so it kind of matches up with our equation we have here. So I is going to be, I is our subscript in this equation. So do we want to start at I equals 1 or I equals 2? Can we start at I equal 1? Is there a problem with doing that? Because we're looking, what do we have in this equation? We have I, and we have I plus 1, right? So we're kind of looking forward in time. So this is like a forward, kind of a forward difference when we did our derivative. So we're okay at starting with I equals 1, because we don't need to look at the time step before. We don't need that information. So we can start at I is equal to 1. So let's start at I equals 1. If we started at I is equal to 2, that also wouldn't be a problem, but we'd be throwing out that first data point where we don't necessarily need to. We can use that first data point. We don't have to throw it out. So we want to start with I equal 1 so we get the most information out of our integration process as we can. So what do we want to increment I by? 1. We're going to go through every value, every time step we have. So we're going to go through every value one at a time. And then what do I want to finish at? What's the last value of I going to be? Length of t. So if I take the length of t, that's going to give me the number of values that I have in my t vector, right? 5, 10, whatever, how many ever things are in my t vector. Is that going to be a problem in this equation? So if t has got 5 values in it, and I goes up to 5, I'm going to plug a 5 in here, so I'm going to say y of 5, y of 5, y of 5. We don't have 6, right? So we don't really want to go all the way to t. We want to go to the length of t minus 1. So to be able to calculate our, or to be able to numerically integrate over just this time span from -1 to +1, I want to go up to the length of t minus 1 so that I don't go beyond that time span that I want to. All right, any questions about that? Okay, so now what do we do inside of this equation? So inside of this for loop. So inside this for loop, we need to put in this equation that we have here. So we're going to go ahead and kind of type that out, and then we'll see if there's any blanks we have to fill in. So we've got y Euler of what? If I want to set this up to kind of mimic what my t vector looks like, my t vector, is it going to be a row vector or is it going to be a column vector? Row vector, because a colon operator always gives us a row vector. So that means it's going to have one row and a whole bunch of columns, right? So I want to kind of set up my y vector to be in the same orientation. That just helps make my code easier. So I'm going to say 1 comma I plus 1. That's my subscript on my y value there. So it's going to be my new value of y is going to be equal to the old value of y. So y Euler 1 row 1 column I plus what? So we have this f of t sub I and f of y sub I. So what is that f? What is that function representing? It's our ordinary differential equation. So we have to use this ordinary differential equation in our Euler's method. So when I'm going to go ahead and call this, I'm going to go ahead and call this my dy dt. So that kind of helps me remember what that is. And now I'm going to have to fill in the blank with that. But we're going to finish this equation out, and then we'll kind of come back to dy dt. What is that? So we need to take dy dt and we need to multiply it by h. We already established what h was up at the top of our code. So that's our equation. Super simple, pretty easy. And now we can just end our for loop. So we got to get back to dy dt. We got to define what dy dt is. So is dy dt going to change? What does dy dt depend on? T, and it could also depend on y. So we kind of have this generic form of t. It could depend on both our independent variable and our dependent variable. In this equation, we only have t on the right-hand side, so we only have that depending on our independent variable t. So if it's going to be changing, if the value of dy dt is going to be changing and it depends on both t and y, where do we want to calculate dy dt? Before our for loop, inside of our for loop, after our for loop? Did you say inside? Why do we want to calculate it inside? Right, because those are going to be values, so t and y are going to be vectors, and y could possibly be changing, right? It's getting updated inside this equation, so we need the most current value of y. So before we calculate the y from our Euler's method, we need to calculate what dy dt is. So we need to get dy dt, and we need to use, kind of apply our equation to calculate what dy dt is. So dy dt is just 2 times t, and t in this case is a vector, right? So we need to tell MATLAB what part of t we want to calculate dy dt with respect to. So in this case, it would be row 1, because we always have one row, and then what column? The I column. Now I set up dy dt to be a scalar value. We could set it up to be a vector. It's not really useful. We don't really need dy dt over the whole, kind of all the different t values. You could set it up as a vector. There's not a problem with that. Just to make sure that if you set it up with a vector on this line here, that you use it as if it was a vector on that line there. So it's kind of easier in my mind to just treat it like a scalar, because we don't really need to keep track of that value. All right, any questions about this so far?
So you don't need to add like one function next to the dy dt and the y here.
Right, because we decided we can leave those as scalars, so we don't need to tell MATLAB what part of dy dt we want to access. So now, after we've run this for loop, we're going to have the values of y. So we're going to have our function y as a function of time over our whole time span that we have. And what we're hoping is that we get something that's going to give us this relationship that says y of t is equal to t squared. So how can we check that? We know what that analytical solution is, so let's kind of, and we can plot them and kind of see what happens side by side. So we need to calculate y from the analytical solution so that we can have something that we want to plot. So let's call this y analytical. And we said, based on our kind of hand calculations that we have, that y analytical is equal to t squared. T is a vector. So what am I going to need? I'm going to need a dot in here to raise it to the second power, right? So now if I want to create a quick plot to kind of compare what those results look like, so I'm going to plot t on my x-axis and y analytical on my y-axis. And then I'm going to also plot my solution from my Euler's method. So I'm going to plot t on my x-axis and then y Euler on my y-axis. And I won't do any labels or anything for the interest of time. So now I'm going to get kind of a plot. It's got 2 curves on it, and we're going to be able to compare how well did we do with we know that the analytical solution is the correct answer. That's the thing that we want to get out of our Euler method. How well does the Euler method do at actually arriving at that analytical solution? So let's go ahead and save this. I'm going to call mine simple Euler. And then if we go and run this, hopefully we did okay. And we can see that we've got 2 different curves here. and they don't line up very well, right? We've got our blue curve, which is our analytical solution, so that's what we know is the correct answer. And we've got our Euler's method, which is the red line there, which is what we estimate as the integral of that equation. We see we didn't get a very good solution, right? The Euler's method and the analytical solution are quite a bit off from each other, right? And you see that they're okay kind of on the left-hand side. So over that first time point, they line up pretty well. But then the errors kind of get bigger and bigger and bigger as we go across our time span. So the Euler method gets worse and worse kind of the more times or the more steps that we have in our system, and how we get farther away from that initial condition. So let's look at, or let's think about, what are some things that could potentially improve this solution? So the only thing that we really kind of have control over when we're doing numerical integration is our step size. So we said that our step size is going to be 0.5. So what if we were to improve that? So what if instead of having 0.5, we would go to 0.1? What do we think this is going to do to our error? Is it going to get better or worse? Better. So we're going to say better. So just like when we were taking the area under the curve, the smaller the step size that we have, kind of the more accurate that our results are going to get. So if we look at what happens now, if we use a step size of 0.1, we can see that our curves are a lot closer to each other, right? We're still not perfect, but our error has improved quite a bit. And if we continue to kind of knock that step size down a little bit, so if I go down to like 0.01, for example, I'm going to get closer and closer. My solutions are going to get closer and closer together. I can keep adding zeros in here, and you can see that to kind of my naked eye, those two lines look like they're on top of each other. If I were to zoom in, they're not perfectly on top of each other. I've still got some error in there. You start adding more and more zeros, and you're going to get to a point where, let's see if we can break. So you guys don't follow this because we're going to break MATLAB in a minute. Eventually we'll get to the point, so if I keep adding zeros, eventually we're going to get to the point where MATLAB's going to yell at me. And it starts to get really slow. So you notice that like the more zeros I add, kind of the longer it takes for that plot to pop up. And now we've gotten to the point of making MATLAB really angry. And it's going to take it forever for the plot to actually pop up. So Euler's method is really simple, but it has a disadvantage in that it's not super accurate. And we have to get to these really small step sizes to really get a good kind of result out of our numerical integration. Let's see if I can really make it mad. So you add too many zeros into your step size, and MATLAB starts giving me these memory allocation errors that it doesn't have enough memory to kind of hold all of that information. And it says, accretion of arrays that are this big, so matrices that have that many values in it, is basically going to make MATLAB mad. So you kind of get to this point of, you're going to be kind of limited in the accuracy that you have. So that's why we have kind of more sophisticated numerical methods or numerical methods to be able to integrate or solve ordinary differential equations. And those are kind of built into MATLAB. So you may have learned in your differential equation classes about Runge-Kutta integrators. And so MATLAB has a whole bunch of those. They're all under the search documentation. They're all functions that start with ODE something or other. The most common one is this ODE 4.5, and that's what we're going to be kind of learning about and using on our final project. And so this function in MATLAB performs fourth order Runge-Kutta integration of ordinary differential equations. We're not going to learn how to do that by hand. You're welcome. But we are going to learn how to we're going to apply this Euler's method to a couple other problems to make sure that we kind of understand what's going on with that. and then it's a very, very similar process. You have to kind of step through to apply a more complicated integration method. All right, so that's all we have for today. Wednesday, we will kind of apply this to the pendulum problem, do an in-class exercise, and give you guys the final project. So that's all we have for today.